This video is part 1 of a review of the tangent function, inverse trig functions, and trig equations and inequalities. These are AP Precalculus topics 3.8 through 3.10. If you appreciate the content, please give it a like. The functions g and h are given by these two expressions. Part 1. Solve g of x equals -1 for all values of x in the domain of g. So g of x is equal to -1, so we will write 2 sine x is equal to -1. Next we isolate the trig function, so we will divide both sides by 2. So that leaves sine x is equal to -1/2. Make sure you have memorized these 9 trig facts. If you haven't, pause the video and memorize them right now. Practice writing the chart on a piece of scratch paper from memory. To solve sine x equals -1/2, we first find the reference angle by sort of ignoring the negative sign and asking ourselves the sine of what is 1/2. Looking at the chart, we know that the sine of pi over 6 is 1/2, so pi over 6 is the reference angle. Sine is the y value on the unit circle, and y values are negative in quadrants 3 and 4. So these are the quadrants where we will find the solutions to this equation. The reference angle is pi over 6, so that means this angle has the size of pi over 6 radians, and so is this angle right here. We think of pi as 6 pi over 6. So this angle right here is 7 pi over 6. So that's one of the solutions. X is equal to 7 pi over 6. We can think of this as 12 pi over 6. So this angle is 11 pi over 6. And that's the other solution. Kabam! Actually, wait, not so fast. These are the solutions on the interval from 0 to 2 pi. But there is no such domain restriction given. We are to find all values of x in the domain of g, and the domain of 2 sine x is from -infinity to +infinity. So we need to somehow express infinitely many solutions. So you can get to another solution from the 7 pi over 6 by adding 2 pi. Adding 2 pi takes you all the way around and back to where you started from. And if I add another 2 pi and another 2 pi, that'll be another solution and another solution. In other words, we can turn this one solution into infinitely many by adding multiples of 2 pi, by adding 2 pi k, where k is any integer. Be sure to write this phrase down as part of your answer. Similarly, we can take the solution of 11 pi over 6 and turn it into infinitely many solutions by adding 2 pi k, where k is any integer. Part 2. Solve h of x equals 5 for values of x in the interval from 0 to pi. So let's see, here's h of x. So h of x equals 5 will be 2 tangent squared x minus 1 is equal to 5. First we do a little algebra to isolate tangent x. We add 1 to both sides, which will be 2 tangent squared x is equal to 6. Then we divide both sides by 2. So that gives tangent squared x is equal to 3. Then we take the square root of both sides. Don't forget the plus or minus when you do this. So we will have the tangent x is equal to plus or minus radical 3. We can determine what the reference angle is going to be by ignoring the plus or minus and asking ourselves the tangent of what is radical 3. Remembering the 9 trig values that we have memorized, the tangent of pi over 3 is radical 3. Therefore, pi over 3 is the reference angle. Since tangent is allowed to be positive or negative this time, normally we would find 4 solutions, 1 in every quadrant. But the domain is limited to the interval from 0 to pi, so we will disregard these 2 solutions. Since the reference angle is pi over 3, this angle in the first quadrant is pi over 3 itself, and thinking of pi as 3 pi over 3, we know that this angle is 2 pi over 3. That's it. These are the 2 solutions on the interval from 0 to pi. Part B. Functions j and k are given by these 2 expressions. B part 1. Solve j of x equals 0 for values in the interval from 0 to 2 pi. So let's set j of x equal to 0. As soon as I see that we have 2 different types of trig functions involved, I know that we are going to have 0 on one side, so this is good, and factor. So the first thing I do is look for a common factor in both terms. And we see that cosine x appears in both terms. So let's factor out a common factor, a GCF, of cosine x. Then it's just a matter of what is left inside the parentheses. I'm showing this now for instructional purposes, but normally we would do the following in our heads. To figure out what goes inside the parentheses, you divide the original expression by the GCF. So we are dividing the first term by cosine x, and we will divide the second term by cosine x. These cosines cancel each other out, leaving behind 2 sine x minus, and these cosines cancel each other out, leaving behind minus radical 3. So we factored it. Next, we can continue solving by setting each one of these factors equal to 0. So we will have the cosine of x is equal to 0. And 2 sine x minus radical 3 is equal to 0. I think you can do the following algebra in your head. I'm going to add radical 3 to both sides and divide by 2. So that gives the sine of x is equal to radical 3 over 2. So I'm going to erase this step. I feel like we can go straight here. Now, where does cosine equal 0? Cosine is the x value on the unit circle, and x values are equal to 0 here and here. So that's at x equals pi over 2 at the top, and at x equals 3 pi over 2 at the bottom. Now, for this other one, we think in terms of a reference angle. So the reference angle is going to be pi over 3. Because the sine of pi over 3 is radical 3 over 2. So that's how we know the reference angle here is pi over 3. Sine is positive in the first quadrant and in the second quadrant because sine is the y value on the unit circle. So in the first quadrant, the solution is pi over 3 itself. So we have x is equal to pi over 3. In the second quadrant, we think of pi as 3 pi over 3. So this angle must be 2 pi over 3. These are the solutions to j of x equals 0 on the interval from 0 to 2 pi. Part 2. Solve k of x equals 8 for values of x in the interval from 0 to 2 pi. Here is k of x again, so let's set this equal to 8. Now let's do a little algebra and isolate the sine x. Subtracting 5 from both sides, we have 4 sine squared x is equal to 3. Dividing both sides by 4, we have sine squared x is equal to 3/4. Taking the square root of both sides, we get sine x is equal to, when you take the square root of a fraction, you take the square root of the numerator and the denominator separately. The square root of 3 can't be simplified, so that's just rad 3. But the square root of 4 is 2. And don't forget, the solutions can be positive or negative whenever you take the square root of both sides of an equation. Let us ponder the reference angle by ignoring the plus or minus and asking ourselves the sine of what is radical 3 over 2. We know that the sine of pi over 3 is radical 3 over 2. So pi over 3 is the reference angle. Since sine is allowed to be positive or negative, we will have solutions in every quadrant. So we will have solutions in quadrant 1 and quadrant 2, quadrant 3, and quadrant 4. So in quadrant 1, the solution is pi over 3 itself. Thinking of pi as 3 pi over 3, the solution in quadrant 2 is x equals 2 pi over 3. In quadrant 3, the solution must be 4 pi over 3. And if this is 3 pi over 3, then 2 pi is 6 pi over 3, making this solution in the fourth quadrant 5 pi over 3. And that's it. These are the 4 solutions to k of x equals 8 on the interval from 0 to 2 pi. Part C. The function m is given by m of x equals radical 3 tangent x plus 1. Find all input values in the domain of m that yield an output value of 0. So that's just a weird way of saying find where m of x is equal to 0. So let's take radical 3 tangent x plus 1 and set that equal to 0. We need to subtract 1 and divide by radical 3. I think we can just do that in our heads. So we get tan x is equal to negative 1 over radical 3. Let's think about the reference angle now by ignoring the negative sign and asking ourselves the tangent of what angle is 1 over radical 3. The tangent of pi over 6 is 1 over radical 3. So pi over 6 is the reference angle. We have learned that the tangent function gives the slope of the terminal side. Since tangent is negative, we will find solutions in the 2 quadrants where the slope is negative. So that's why quadrants 2 and 4 will give us the solutions. Since the reference angle is pi over 6, we will think of pi as 6 pi over 6. So this angle in the second quadrant is 5 pi over 6. Over here at 2 pi, this can be thought of as 12 pi over 6. So this angle in the fourth quadrant is 11 pi over 6. And that's it. These are the 2 angles where the output value is 0. Be careful, do not do what I almost did. The domain was not limited to the interval from 0 to 2 pi. We are to find all input values in the domain of M. So we need to somehow turn these two solutions into an expression representing the infinitely many solutions that we get as we go around and around the unit circle. On a previous problem, we found infinitely many solutions by taking the two solutions on the interval from 0 to 2 pi and adding 2 pi k to each one, where k is any integer. However, when the two solutions are directly across from each other, we can represent the infinitely many solutions with one equation. We don't need two separate little equations. That's because if we start from the first solution, which is 5 pi over 6, we can get the next solution by adding pi. This is a semicircle, so pi radians. And if we add pi again, that takes us back to this position, which will be another solution. So we don't have to go all the way around and back to the starting point. We don't have to add 2 pi to get from one solution to the next. We have to add multiples of pi, 1 pi, 2 pi, 3 pi, 4 pi. So whenever you have two solutions that are directly across from each other, you don't make two separate equations, you just make one. And instead of adding multiples of 2 pi, you simply add multiples of pi. So we will add pi k, where k is any integer. So that's it for part C. Number 2, the function k is given by k of x equals the tangent of 1/2 x. Which of the following gives the vertical asymptotes of k? In your head, you should be thinking tangent is sine over cosine. And a vertical asymptote will occur wherever the denominator is equal to 0, because you can't divide by 0. So we will have a vertical asymptote where the cosine of 1/2 x is equal to 0. First, we solve for the inside expression by asking ourselves, where does cosine equal 0? Cosine is the x value on the unit circle, and x values will equal 0 here and here. So that's at pi over 2 and 3 pi over 2. However, that's on the interval from 0 to 2 pi. We are not being given a domain limitation, so we need to somehow come up with an expression representing the infinitely many solutions to this equation. Since the solutions are directly across from each other, we can get from one solution to the next solution by adding pi. In other words, we can get infinitely many solutions by adding multiples of pi. So instead of making a little list, we write the first solution and then we add pi k, where k is any integer. Now we just need to solve for x by multiplying both sides of this equation by 2. We need to be sure to multiply each term by 2. So x will equal, and 2 pi over 2 is just pi, and then plus 2 pi k. So there it is, pi plus 2 pi k, where k is any integer. And the answer is C. Number 3 is just like number 2. We need to find an expression for the vertical asymptotes of tangent pi x. Tangent is sine over cosine. The vertical asymptotes will be where the denominator, cosine pi x, is equal to 0. We start by solving for the inside part, pi x. Where does cosine equal 0? Pi over 2 and 3 pi over 2. But again, we can get to one solution to the next by adding pi radians. So we put the first solution of pi over 2, and then we add pi k, where k is any integer. Finally, we divide everything by pi to get x by itself. This would be pi over 2 pi, and the pi's cancel out, leaving 1/2. and dividing this term by pi just leaves k. So we're looking for 1/2 plus k, where k is any integer, and the answer is C. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.